Okay, what we have here is a simple spring scale, it's called, as if you caught a fish and we're weighing it. It measures force, in this case in grams. And we've got 3 of these guys set up, and notice they are not moving. Alright, this is in a state of equilibrium. I've got that knot right there, and if you look, it is directly over a dot. And I've measured the angle here. You can see directly through that loop there's another dot. I recorded the weight, the force of the tension on the string on each of these scales, and we're going to use this to represent vectors. Alright, so I'm going to get the camera mounted here so you can see what I'm doing. Hopefully that's not too crooked. Alright, so like I said, this is an equilibrium. It is not moving. We can record the angles and the tension on each of these. I've done every one but this third one here. Looking straight down. Okay. The tension on this one right here is 890 grams. And on this one here it is about 770. It's quite difficult to read. And on this one over here, it's about 1030. Okay, so varying tensions. Now the idea is that because it's not moving, the forces are all balanced out. They should be equal and opposite if I consider any 2 of these in opposition to the third one. So we're going to disconnect this here. Alright, and we're going to use a few of our weapons of math instruction. We're going to draw some lines, measure some angles. Now we could imagine that maybe this is the vector that's representing like a weight hanging on a string, so straight down. So maybe we'll consider this vertically straight down, and 890 is going to be 8.9 centimeters. Actually, let's double that. So that's going to be about 17.8, which is almost exactly what I have measured this to be. So that is going to be right there. Alright, so I'm going to make that vector right there. So 17.8 going in that direction. And then in this direction, same thing, but it's going to be going 1030, so that would be 2060, 20.6. And that is to right there. Okay, so I'll draw that vector. And then the third one is 770, so what that's 15.4. Okay, so we can compare these vectors 2 ways. One is the simple sort of geometric way, where we are going to just do the parallelogram method. Okay, now to do that, what I'm going to do is draw a parallel to this side up here, and a parallel to this side right here. Let me get a few more. Alright, here we go. So these are kind of handy when drawing parallels. It's an old architect's trick. If I put a triangle like this that is right along that line, okay, so I line it up with what I want to be parallel to, and then I can slide this up. I keep moving that, whoops, that's not very good. If I line this up right here, and I'm going to actually do it down here. So I've drawn it rather big. Okay, so if I line that up like that, then I can slide this forward until it gets to the end right there. See that? That will be parallel to right here because of the corresponding angles rule. Alright? So I'll get that super accurate, slide that up right there to the very, very tip. Alright, now draw my parallel. I'm going to continue it, and that will see it go right to the tip. So I'm going to continue this in that line parallel. Okay, and I'll do the same thing over here to this one. Now this is going to be a little bit trickier because I'm going to slide it a longer direction, but we'll see if we can make this work. So it's like this, and then I'm going to slide like that forward, slide that one forward, slide it forward again, keep working my way up there. I guess I can flip this over to this side. This is a bit unorthodox. Let's slide it like that, and there will be my parallel right there at that very tip. So if I draw this to help me orient it, and then there's the parallel coming to that tip. Now that I've got that established, I can move it over here. Okay, so this is the parallelogram method. I pick up this vector, I put it right there. That's where it would be, coming in like that. I could pick up this vector, put it right there. There it would be. The arrowheads meet right there. Where the two arrowheads meet, then this is the resultant vector that I draw. Okay. Now the question is this vector the exact equal and opposite of this one? All right. So we should be able to tell that by simply extending this. It should be in the exact opposite direction. We'll see how close we are. And it looks like it's very, very close. It's nice to have visual confirmation. Look at that. Now the question is this 890? So that's going to be 780. Wish the camera could zoom in, but I'm putting it right there. And it is, well, there's 18, and that is exactly, almost exactly 780. Alright? So there it is, sort of geometrical proof that this vector here, this resultant, when I add vector A right there and vector B right here, that this is A plus B. And that's equal and opposite to this one. Alright. Now we can also think of this as a second way, more sort of, if you're thinking in terms of physics, where if this is our object that's hanging straight down, alright, and maybe these are two strings that are attached to a wall, and we're going to then break each of these vectors down and add them up in rectangular form. Okay, so if I put the 45, 45, 90 triangle like this and establish a right angle. Remember, we're trying to imagine that this is now a weight that's hanging straight down. Okay, so if I'm going to now resolve these vectors, this will be my horizontal line, like that. Okay, and I'm going to break this down into two components, the horizontal part and the vertical part for each of these two. To do that, I need to measure the angle. Okay, so by doing this right here, lining it up as carefully as I can along the 0 like this, is an angle of about, there's 10, there's 20, that looks like that's about 13 degrees. Okay, and it's, again, we'll call this a length of 770. And this one has an angle of about 44 degrees. So that is 44 degrees like this. If that's 44 degrees, then this angle right here is 136 degrees. So remember, we're thinking about vectors in terms of polar coordinates. So this one is 13 degrees like this, and this one is 136 degrees, and then this one is at 1030. Okay? So if I get the calculator out and resolve those, I can take 1030 and multiply that times first the cosine of 136, and I get that the horizontal component, that's this part here, the x direction, is going to be negative 740, and it's going to be the part that's directly below that, like that. That's the x amount. So that negative 740.9. Then we'll do the vertical component. That's how much this vector is going straight up, and that'll be equivalent to coming over here. And if I do then 1030 times the sine of 136, I get 715.5 when I round it. Okay, I do the same thing with 13 degrees, so I do 770 times sine of, or I'll do cosine first, cosine of 13, and I get 750. So this horizontal part is almost the entire strength of that vector. Whoops, I'm going all the way out to here. So here the x component is equal to 750.3. And then the vertical component is going to be 770 times the sine of 13 degrees. Okay? And that's 173. So this vertical component, I'll put it right here. This vertical component is 173.2. All right? So if I put those in rectangular form, then that's the thing about resolving vectors, is breaking them down into the x and y parts. I've got negative 740.9 comma 715.5. That's the vector A. And vector B is 750.3 and 173.2. That then if I just add these, I get the sum of these in rectangular form. So this is going to be 0.7888. That's kind of a convenient number. And this one, this is a negative, all right? So it's going to be, when I take that away, this is going to be 9.4. So they almost exactly cancel each other out. And they're supposed to do that. They're supposed to be very nearly canceling, because it's in equilibrium. It's not moving left or right. So that's really my amount of error. This is the number that's supposed to correspond to be equal and opposite this. And there it is. So that shows how resolving vectors and breaking them down shows that these very nearly cancel each other out, and these together combine to be equal and opposite that one. All right, that's our little vector demonstration for the day.